Hi everyone, I'm Philipp. I want to talk a bit about search and trying to get you into search. So I work for Elastic, the company behind Elasticsearch. We also do a lot in the search space. My official title I think is now developer advocate. I'm in engineering, I do lots of stuff, but I also do a lot of conferences just to talk about the fun stuff that we do. Yeah, that's what I do. So who uses databases? I guess pretty much everybody. Good. Who uses search already? Who uses Elasticsearch? Good. Who uses some other search? Who uses something based on Lucene? Other than Elasticsearch. Okay, that's quite a few. Who uses some entirely different search? What are you using? Algolia. Algolia, okay, search as a service, but you cannot really see into the details that much. I want to look a bit behind the scenes today. So yes, you can use various things as a service, but we want to look a bit behind what is going on. So I always compare search and databases to this thing that is a bit black and white here. This is the database side basically, and this is the search side. So databases are very much black and white. You store something and you want to retrieve it, and you're mostly looking for direct hits. You can do some search like a like search with the percentages, but that will be normally very slow and also doesn't have all the bells and whistles that you might want. Whereas search is more like these shades of gray. It might not be like the exact thing you want to search for example. You might not care about singular or plural, or you might not even care about adjective or noun. You might just be interested in the concept that you're searching for. And then you have these shades of gray, which is also the quality. Because while a database just gives you the results, search is much more about like, oh, I have something in a specific quality. And we'll dive into how to calculate that quality and what that actually means. So to get started, just to give a quick idea what you generally do with search. So when you search, let's assume we have our web shop here and you start searching, and I'm searching for a white shirt, for example, and you can see, oh, we have an auto-completion, that's nice. I'll just click on the auto-completion and then our search is working. Is this a very good search result for a white shirt? Probably not. Since this is our own custom thing here, we can actually tune the parameters. So basically we can see what this is doing behind the scenes. And it doesn't really matter so much of what I'm doing. It's more about the idea that search is insofar a very interesting problem because it's very much like not just a technical solution, but it's very much like what data do you have and what do your users actually expect to get back. It's not, you can have the technically correct answer, but if your users expect something differently, they will still not be very happy with your search. So for example here, I'll just switch this parameter and apply that. And then hopefully my search is getting better for white shirt. And then the other thing is like, is this, since you can see I'm logged in with my username and everything, is this very relevant for me when I search that? So for example, the very first shirt is female. Like, that is probably not what I was interested in. So do I want to search for myself or my girlfriend? So it might be a difference of what you want to return. So for example, you could say we have here somewhere, we have a gender bias, which will basically say, gender bias 100 will basically mean since I have stored my own gender, it will only show me stuff for my gender. And if I apply that, then you can see I'm only getting the male shirts back now. So this is probably more relevant. But there are a lot of things you can tune, and while I can show you some tech parts, like figuring out what your data you have and what your users are expecting, that is something you will need to figure out. That was also what makes search kind of an interesting problem. So, when you search, you generally do more work up front when you store things. So generally, the thing that is storing everything on disk is Apache Lucene. So there is no other database or data stores involved here. Apache Lucene is writing to disk and is actually doing the search part. Elasticsearch is kind of like the shell around it. So it does the REST API, the query DSL, it does the distribution and replication of data. So you interact with Elasticsearch, but what is actually doing the search part here is Lucene in the background. But we'll use Elasticsearch as an example. So, what is the phrase he's saying here? Yes, exactly. And this is the sentence we want to use for our example. So these are not the droids you're looking for. And for example, we'll assume we have this emphasis tag here. So this is, we will emphasize the not. And we want to see what is actually being stored when you search for this. What are we doing here? A database would pretty much just take this, store that, and afterwards you would try to search. Whereas full text search is more concerned with doing more work up front to make this work. So the first thing you normally do is you throw out any formatting because nobody is searching for that emphasis. We'll just kick it out since we assume it doesn't make any difference. Next up, we're tokenizing. Tokenizing in most languages, which are not Japanese and Chinese, for example, are rather simple. It's just white spaces and punctuation marks. So I've made a little more space here. You can see that the dot at the end is gone. So basically, each of these words is now a token. And we'll just work on independent tokens. Next up, we are lowercasing everything because normally you don't care about upper and lowercase. Like if you search on Google, you probably don't properly lowercase and uppercase stuff. So we'll just lowercase everything so we don't need to make the distinction anymore. Next up, keep in mind, these are not the droids you're looking for. We're removing the so-called stop words. And the stop words are very common words that appear pretty much everywhere. So there's very little value in storing them because you would find everything with them. So these are, for example, very common words, and we're just kicking them out. So we're just keeping these 3 tokens here from our entire sentence. The rest we are not storing by the way I'm analyzing this here. And the final step then is I want to stem. Stemming basically means throw out or you want to reduce to the word root or stem. So for example, droid, I don't care about singular or plural. For the verb, look, looks, looking, I don't really care about which specific flexion I have here. I just want the concept. So I will stem that down to these droid, you look. These are the 3 tokens I want to extract in the end. So you can actually try that out hands-on. Let's do that hands-on. So I have Kibana running here. And this is console. You see you have syntax highlighting, you would have auto-completion. You can basically just run your queries and try out stuff as you go along. So for example here, with _analyze, I'm not storing anything. I'm just trying out what would happen if I was storing that sentence. So here I say, these are not the droids you're looking for, so I'm trying out this sentence. So if I run that, you can see droid, you, look. These are the exactly 3 terms I've shown you before, plus some more information. So for example, you see we have a position. The position is very handy if you do a phrase search afterwards. So for example, if you're searching for the phrase droid you, which is a weird phrase, but let's assume you're searching for droid you can just make sure we have both tokens, and then you make sure one is followed by the other one. And that will make your search very efficient afterwards. You also have a start and an end offset. That will be very handy if you highlight your hits. So if you have a long text and you want to highlight, oh, this is your search term you have been searching for, that is what you can be using to do that. You can also define your entire pipeline here. So here I'm defining the HTML strip, the standard tokenizer, lowercase stop word snowball with the same sentence, gives you the exact same result. Probably no big surprises for that. Okay, stop words. The list of stop words in English is surprisingly small. This is like 33, 35, I always forget. But this is just a handful of words. Like that our one sentence had so many of these stop words was just pure coincidence, basically. You can disable stop words. You can provide your own list of stop words if that makes more sense for you. This is where you can find the stop words in the source code, so that is pretty well hidden. But this is where the stop words are living and you could find them. So, should you always use stop words? Yes, no, maybe. Yes, the answer is always it depends. But there are things that you will not be able to find if you use stop words. For example, if you have to be or not to be, these are all stop words. So there is nothing that we will store. So yeah, Shakespeare's phrase there, you will not be able to find that if you use the standard pipeline. So you will probably need to customize that. So there are scenarios where removing all the stop words is not that helpful, but it will depend, and you will probably need to combine multiple approaches. Okay, so I was told that this is kind of the right phrase in Armenian. I hope. Yeah, yes, kind of. Okay. because Elasticsearch does support Armenian. And unfortunately for me, this is pretty much a black box because I don't know what I have here and I throw something in. So this is our phrase. Any guesses what will happen if we run that through stopwords and stemming? And I have the feeling it's not doing too much. Because when I tried that, this is what I got. So I think the first token, there is some ending cut off, but otherwise it's pretty much the same, which I'm not sure if that is what it's supposed to be or if it's just not very good. But this is what you get in Armenian. What happens if you use the English analyzer on Armenian texts? Nothing good, because the rules don't apply. So you will pretty much get out the original sentence again. So that is what you will get. If you wonder where the Armenian stopwords are, they're also pretty well hidden, but yeah, this is where you can find them, very well hidden. Other languages, we supported quite a lot of languages. For example, for Russian, I also don't speak Russian, so I will not try. This, I think, is the same phrase in Russian. Russian seems to work a little better, so if you run that through the analyzer, this is what remains. Which is maybe kind of, but I don't really know. I'm always asking people, normally I try Google Translate and then Google Translate fails and then I ask the local and then they show me what the right phrase is. Okay, the Russian stopwords are somewhere else. They're hidden here, but yeah, this is where you could find the stopwords for that. What happens if you don't know the language? You need to know, because Elasticsearch by default does not figure out which language you have. So one of my colleagues, Alex from Munich, he wrote a plugin to actually try to detect the language for a string. Because oftentimes you don't know a user, there's a field and you don't know, are the users providing the response in Armenian or Russian, for example. But to properly store it and analyze it, you will need to know the language. So this is one of the plugins that you can use to actually detect the language and then figure out, okay, probably I want to use this analyzer on that. These are all the languages that we're supporting. There are quite a lot. Though, for example, Slovenian and Slovakian in Europe are not supported because, I don't know, nobody has done the work. There are also more plugins. So, for example, if you use Asian languages, they're kind of complicated and a lot of people don't use them. So we don't package them in because A, the downloads would be bigger, and B, you would need to load more things into memory. So, for example, Asian languages, but also complicated languages like Polish, are extra plugins. Also, depending on how complex your language is or how many flexions you have, stemming will work better or worse. For example, English is pretty simple. So for English, the stemming works reasonably well. For more complex languages like Russian, it doesn't work that well because there's too much variation and it doesn't pick all of that up. Yeah, and the community is also providing some of those. So for example, if you need Hebrew, there's only a community plugin for that. And language rules totally depend on the language, but that's probably not that surprising. So for example, in English, this is, has, or possessive, the S, that is just thrown out because we assume it doesn't have any meaning. In French, for example, we have the article in the beginning and the accent, and we just kick those out because we assume those don't make any difference here. In German, we have these weird umlauts and that special S thingy here. Those don't have much meaning, so here you can see the umlaut is just removed and that special S is just a double S. But umlauts, for example, in some languages are making a real difference. So for example, I think that in Swedish you have an A with the umlaut as well, and there it's a totally different letter. And I tried. For Swedish, the umlaut is not removed. There you keep the original sentence, not the original character. Okay. Obi-Wan never told you what happened to your father. I'll come back to English so I can also participate in this. What remains if I run that through the same pipeline? Your father. Okay. How many tokens will Obi-Wan be? 2? Yeah, that depends. So that's then the tokenizer. With the standard tokenizer, what you will end up with is these tokens. So Obi-Wan is, with the standard analyzer, will be broken up. You can see here, this is what remains. So in this example, we don't have that many stop words, but this is more of a coincidence. Just this is what remains. Another example, no, I am your father. What remains of this sentence? Any guesses? Yeah, it's actually I am your father, because the other ones are not stop words. And here you can also see something, 10 minutes? Okay, I'll continue. Here you can see something else that is very interesting. Elasticsearch is search. It doesn't understand your sentence. It's not natural language processing because we have kicked out the no. And it doesn't know, am I your father or am I not your father? But search doesn't really care about that. It's just matching on tokens. So it doesn't understand your sentences. If something is good or bad, yes, no, it doesn't really care. It's just trying to match similar tokens. This is what you're doing here. The data structure that we're storing behind the scenes then is called the inverted index. So basically what you get is we extract all the tokens from our sentences. So I've stored all 3 sentences, or I'm storing all 3 sentences here. These are all the tokens that we have extracted, alphabetically sorted. So searching for something will be very quick because you basically just have to find the right entrance in this list, alphabetically sorted, and then you can check like which documents contain this specific token. And then you store like how many times does my token appear and at what position. And with that information, you can do searches very efficiently. And you can also do like an AND or an OR search for multiple terms. Is also very simple because you can just AND or connect the lines to actually find what you have been searching for. So let's do something actual because so far we've just tried to analyze stuff. So I will create a so-called mapping. So what we are doing here is I'm adding a few more things. So for example, I'm adding a thing called I just call this like that, my synonym filter. And here I'm defining 2 synonyms. So for example, I say father and dad, they are the same. So if somewhere is father, dad should also be found and the other way around. Whereas for droid, I say if there is droid somewhere, I want to find this if somebody searches for droid or if somebody searches for machine. Because every droid is a machine, but not every machine is a droid. So it's only like one way or replacement. And then we're running through the same pipeline. So you can see here, we're doing the HTML scripts, standard, tokenizer, lowercase, stopword, snowball. And at the very end, we're applying our synonyms. And then I'm actually saying I have a field called quote. And in that field is of the type text. And I want to analyze this with the my analyzer. So let's insert that mapping. That is pretty much like a schema in the relational world. But this defines what we have here. And you can actually see I have my field quote here, which is text and uses my analyzer. And then we can throw in 3 documents. So the 3 documents that we've covered so far, we are adding those here. Now you could retrieve those. And you can see here, I've stored that under the ID 1. I've gotten back that document. These are not the droids you're looking for, plus some meta information. So you can see I have the index name, I have a type, I have an ID, I have a version, and the whole thing has been found. You can also use this pretty much like a database. If you add underscore source, you can see you just get back what you have stored originally. So you can use this more or less like a database, but this is really not the point. We want to do search. So what would be the SQL equivalent of this query here? Yes?
From Star Wars.
Yes, exactly. That's a select star from Star Wars. Or select asterisk from Star Wars. And then we're getting back our 3 documents. What happens if we search for droid? How many documents will we get back? 1. Because there was only one document that contained. These are not the droids you're looking for. What happens if I search for dad? How many documents will be found? 2. There was father, but we have a synonym. So we will find, no, I am your father, and Obi-Wan never told you what happened to your father. So these are the 2 that we're getting back here. You can also get explained why something is matching or why something is not matching. So for example, here I'm taking my document 0 and run explain on it. And it will tell me it didn't match. Okay, what if I change that to 1? Will that find something or will that not find something? Yeah, it will not find something. but it's telling you something different. Why? Because I started indexing at 1. So 0 was the document, 0 didn't exist, the document didn't exist. That was the error message for that. But for example, the documents 2 and 3 I should find here. So if I run those, it will actually tell you, okay, this document, so this is the query you've been running, and basically we're checking why does or does not this specific document match. And then it will tell you why it's matching or not matching. What happens if I search for machine? Should I find something or should I not find something? Yes. Every droid is a machine, but not every machine is a droid. So we should find the droid in this example here. We can also do something like a phrase search. For example, here I'm searching for I am your father. And if I run that, you can see I am your father. We have this exact phrase here. You can also add a so-called slop. So what you generally have is in that the phrase query, all the tokens in your query need to be there. The slop basically means in the document that you're searching for, there can be something else in there as well. So when I'm searching for that, I am your father, you will find something. If I search for I am not your father, will I find something, yes or no?
No.
I find something.
No.
Let's try another one. I am your loving father. Will I find something now or not? No. So why was the not working and the loving doesn't?
Because no and no are...
Yes, no and not are stop words, so we're removing those. And because I have this slop, which basically means there can be something else there, that's why there was something matching. So you need to always be careful with stop words. They can give you kind of unexpected results. You can also do something like this, a fuzzy search. A fuzzy search, for example, you don't know how to spell one. So from Obi-Wan, you forgot how to spell that. So if you're searching for that, you see Obi-Wan never told you what happened to your father. I'm still finding that even though I have misspelled one. And the fuzziness auto, so basically fuzziness is a Levenstein distance. The Levenstein distance is, assume Levenstein distance of 1, one letter too much, missing, or different. With the auto fuzziness, that auto fuzziness for this query here would mean 1, because the fuzziness auto is dependent on the query length. So 0 to 2 characters would give you an auto fuzziness of 0, 3 to 5 characters 1, and more than 5 characters would give you a fuzziness of 2. We generally don't do more than fuzziness 2 because then you would find a lot of things that you don't really want to find anymore. What happens if I search for this? So I have Ovi and Van, and both are misspelled, and I search with fuzziness of 1. Will I find something, yes or no? Yeah, that's the question. And you will find something because, yes, the fuzziness is on a per token level and not globally, which you need to know, I guess. Otherwise, yeah, you're just confused. So we have covered a lot of stuff. By the way, how we are calculating the fuzziness is, initially we did some brute force approach, but now we use some fine data structure called Levenstein automaton, which looks something like this. So for example, here we're searching for food, and going horizontally, we're having a match. And this has a fuzziness of 2, so going up is one of the edits, basically. So one of the letters that is missing, too much, or different. And you can see this is basically, we want to find the path from the bottom left to the top right corner. And automaton, which makes the search or this fuzziness search very efficient in the background. You could also do the same thing with a relational database, which would look something like this, but this is not going to be a lot of fun. And also with the wildcard in the beginning, it will not be very fast because, well, you cannot use an index. You need a full table scan. So, scoring. Something we've always had, and we didn't really cover on yet, was we have this score. So every time we are finding something, there is a score. This is pretty much the quality of how good is the match that we're having here. And the score is being calculated by a fancy data structure called term frequency inverse document frequency, or an algorithm, or TF-IDF in short, if you search for one term. Actually, the current implementation we're using is different or slightly different. It's called BM25, which stands for Best Match 25. So it's the 25th iteration of a best match algorithm. We might have an improvement like BM30 or I don't know, whatever number at some point, maybe. But currently, this is the default what you're using. But the main differences between TF-IDF and BM25 are that the kind of like the parameters are slightly different. But I'll show you. So TF-IDF consists of three main parts. The first one is the term frequency, which basically means you're searching for a term, and the more often your term appears in a document, the more relevant it is. So for example, if you're searching for droid, and one field contains droid 5 times, it's more relevant than a field that contains droid just once. Which looks something like this. So for TF-IDF, you can see here, this is the number of occurrences. So if something appears once, the score is rather low. If something appears 5 times, the score is higher. The main difference here is that you can see TF-IDF assumes this will grow forever, whereas BM25 pretty much assumes once you hit 5 matches in one field, it doesn't get much more important anymore. So we're just like plateauing that curve at some point. You could tweak that through parameters as well, but normally the defaults are kind of good. Next thing is inverse document frequency, which basically says the rarer a token or a term is over all the documents you have, the more valuable it is. So basically, it dampens the importance of very common terms, which looks something like this. So if your term is appearing just a few times over all your documents, it has a very high score. Whereas if a value appears loads of times, like the score of that is decreasing. So it's kind of like dampening that if it's not that common. No, it's just to kind of, the main thing is if you're searching for multiple terms and one of them is very common and one of them is very rare, to kind of like weigh them accordingly. So that the one that is very rare should make or should have a higher impact than the one that is very common. That is normally giving you more relevant results, hopefully. But the general assumption is if something is rare, it's kind of like important and you want to find that. If something is very common, it doesn't add that much value because it's everywhere anyway. So this is kind of the calculation that you do there. And the final thing we're doing is the so-called field length norm, which basically says the shorter the field and your term is there, the more important. So basically, you're taking 1 divided by the number of terms in the field, and that gives you the field length norm. So if you run that query, it will actually show you all the different pieces of how you calculated that. So you can see, okay, here we are calculating the value for IDF, and here we have a term frequency norm, and here we have a term frequency. So you get all the different pieces and how we calculated what the score is. So if you're unsure why a document has a higher or lower score, with the explain, you can actually check why is that score like that and look a bit into the internals. So for example, if I'm searching for father over the 3 documents that we had, we have this one, I am your father, has this score. Whereas Obi-Wan never told you what happened to your father, has this score. Why is this ranked higher than the other one? Yes, the only difference is the length, because both contain father once, so that is the same. Both are searching for father, so the IDF is also the same for them. The only thing that is there, or the only difference, is the inverse document, the field length norm. So the length or the number of tokens. And you can see the difference is rather minor. So this is how we have scored that. This was true for searching for one term. What happens if you search for multiple ones? So for example, I assume I'm searching for your father now. And this is made up, so this is just for the explanation here. And I assume that your is very common in Star Wars and father is very rare in Star Wars. So we'll assume here that your basically has a value of 1 and father has a value of 5. If you're searching for both terms, the ideal document that you find contains both of them. So this is this vector here. But then you want to know which documents are more relevant, the ones that only contain your or the ones that only contain father. And to kind of make that distinction, we are calculating that angle between these vectors here, and the shorter that angle, the more relevant it is. So here you would see like the best matches would be containing your and father, but the next best ones would be father, and only then would be the documents containing your. That is how you compare those. You also have a coordination factor, which basically rewards having more terms in a search result, which looks something like this. So for example, if you're searching for 3 terms, you have like you don't only sum up the individual scores, but you only also multiply them of how many of your terms are there. So 1/3, 2/3, or 3/3 of the terms are there to kind of reward having more of the results there. And you can put all of that together in the practical scoring function, which looks something like this. And we've basically covered all of them. So you can also add a boost and say a specific term or field is more important than others. But the rest you have seen: term frequency, inverse document frequency, the norm, the coordination factor, and the query norm. So these are all the components that you have to actually make your search work. And you can also override that with providing your own function score. So for example, you could say, I have something, like if you have a news site, probably you want to rank the more recent articles higher, because in news, like what has happened today is more relevant than yesterday, and what happened a week ago is probably not relevant at all anymore. So for that, you could have a decaying function based on a date, or you could do the same for geo-distances. So for example, if you're searching for restaurants, there would be a contributing factor of how close is it to you, and then just decaying out stuff that is further away. Kind of the simplest one is if I run this, I search for father, but I give it a random score. So the order of that would just be random and could also change at any point in time. So this one here, so you can see, depending on what query you run, you will get different results and different scores. When might this be helpful? When could you use that? Yeah, so sometimes you want like some random samples. So you have lots of documents which would match this, and you just want to have a random sample of the top 10 or whatever documents. The other thing that what I'm sometimes doing is when you're sponsoring a conference and you're giving away a prize at the end, you need to find a lucky winner. And we use this to actually find the lucky winner. Because what you can do is here, you can add a parameter called size. And then you can say size 1, and that would basically give you one lucky winner out of all the people that have entered your prize draw. So that is one of the more practical things to do with that. Okay, something a lot of people try to do, what does not work well, is translating that score to percentages. Because a lot of people say, okay, this is a 100% perfect score, and this is a 50% match, for example. This does not work, and the documentation from Lucene is also pretty clear about that, and says don't do this, seriously. So they have their own page, scores as percentages. Don't do that. A lot of people have tried, a lot of people have failed, and I can actually show you why this might be a really bad idea. So for example, let's say these are my father's machines. So we're storing a sentence. What happens if I analyze that? You get my father, dad, you can see there the synonym is at work, and machine. Droids are machines, but not all machines are droids. So here we only have machines and not droids, right? So these are the tokens that we're extracting. So I will actually store that document as the fourth document. And you see the tokens that we have extracted were my father machine. And then I'm searching for my father machine. So this is like a 100% match, right? All the tokens that we have stored are in our search query. So then you will get out a score for this one for 2.9 something. And the next result is only 0.8 something. So you would assume, or we could say this is 100%, right? You agree? 100%? I'm dead. No worries. Thank you. But no, this is working. Awesome. So we could assume this is 100%, right? And so we say 29 something, that is 100%. The problem is what happens if I delete that document? And then I search again, and then you will have that other thing, which now the score changed because the other document is not there anymore, is now 1.2 something. Is that now the new 100%, or is this like a 43%? I think 43 is the right number. Is this like a 43% hit now? Is it 100%? Is it 43? Yeah. Yeah, like this is very hard. Like these comparisons don't make much sense, because what happens if you now add another document? So here, this might be slightly constructed, but these droids are my father's machines. And if I'm searching for the same thing, What will be the score of this? Will this be higher than the first document? No, it will be higher. Because the term frequency is we have father twice, and we have droid machine, which will basically both map to machine, are also there twice. So the score should be higher. And then, so you can see suddenly now I have a 3-point something score. And now suddenly you have like a 103% match. So this trying to calculate that to percentages will just not work because you cannot compare it. And normally a score is only relevant within one query, but it doesn't make sense to compare it across queries because they're just not comparable. So don't do that. This is not going to work out well. OK. Anybody knows the number of default charts that we are having right now? 5, right? You were aware that we will change it in the next major version. So we will change that to 1 in the next major version, which will also have some good effects because of this IDF. How many times does a term appear? That was always calculated on a per shard level by default, and that could be slightly skewed. So you're avoiding that problem. And basically, you could force Elasticsearch. Perfect now. You could force Elasticsearch to actually make these IDF statistics across all the shards the same with this special command. But you don't want to do that because it is really not required. But that is something you might run into. If you have very little data, your data might be slightly skewed. But normally you have a lot of data, then your search results will be pretty good and evened out. OK. People are often asking performance. How does this compare to other systems? And this is my favorite comic for performance questions. Because whenever somebody does a benchmark for their own system and somebody else, this is basically what they're doing. So whenever you get somebody's performance benchmarks, assume that it's something like this, that you found similar conditions which are very favorable for your own product, but very unfavorable for anybody else's products. So that's why we are not doing any benchmarks with competitors. You can benchmark like how well is one system working for your data on your hardware for your queries. How well is that working? But don't believe in any other benchmarks because they're normally just made up and will look something like this, and they're just not reality. The other thing is people are coming to me and say like, oh, we have a huge use case. We have 1 million documents. And this is pretty much our feeling when somebody says like 1 million documents, because that is pretty much what Elasticsearch eats for breakfast. And with 1 million documents, you have lots of options of what you can do. You don't really need to worry about scaling or anything. You can try a lot of experimentations because it will work very nicely. So to wrap up and leave some time for questions, we've pretty much seen when you store something, we're doing more work than a database. We're basically kicking out the formatting. We're tokenizing. Depending on the tokenizer, the dash will be removed and broken up into 2 tokens or not. We lowercase, we remove the stop words, we do the stemming to the word stem, which might not work that well for Armenian, admittedly, but maybe we can improve that at some point. And you can optionally add synonyms. Synonyms we don't provide. You will always need to provide your own synonym list because that's very dependent on your domain and what you're trying to do. You might find synonym lists for your domain or could use WordNet data, or I've also heard that some people had very good results of just looking up the type or the things, the redirects on Wikipedia, because they know a lot of typos and things that are related. So if you have kind of a more generic domain, that might be a good synonym list. But otherwise, you will need to create that synonym list yourself. We've looked into scoring, like term frequency, inverse document frequency, field length norm, and then the vector space model. There are more advanced things that we didn't cover today. So for example, you could highlight the specific where you had your hit. You could break stuff into smaller parts to find like just more like partial matches. So for example, if you have the term blueberry in your index right now, and you're searching for blue, you wouldn't find that because blue and blueberry, they're just 2 different words. And we don't have a dictionary to know that blue is its own word, and we should break that out. For that, you might want to use n-grams, which basically takes out groups of letters of 3, but that is configurable. 3 is kind of common. And then you just try to find these sub-matches. You can store your data in multiple ways. So once you just lowercase everything and store it, once you remove the stop words, that would, for example, help you with the to be or not to be, which was just stop words. So if you would store stuff in multiple ways and search across of them to find the best matches. And then, yeah, you can do stuff to change your mappings and change your analysis pipeline with reindex and all of this is also in the slide deck. I'll publish the slide deck afterwards, and you can see way more examples. Like I have nearly another hour in this talk, just more advanced queries. By the way, if you want to use this for more, our stack can kind of do analytics. So for example, for the web shop that I've shown in the beginning, these are analytics for the web shop. So for example, you can see which products are very well reviewed, or you can see where you have manufacturing bugs, or where you're selling stuff or you're not selling stuff, or how recommendations work out, and what is currently kind of like what people are doing on the reviews. So this is more not just search, but it can do analytics and lots of other things as well. If you don't want to build all of that yourself, and you just want to use a product that does that under the hood for you, we have recently acquired another company called SwiftType, which is basically search as a service. So that can crawl your website, or you can use their API. You just throw your stuff there. It will provide the search for you, and you could then tune it through a UI. So you don't need to create all the queries yourself. And this is basically, or that is using Elasticsearch under the hood, and it's doing pretty much of what we have discussed today as well. And with that, I think we have probably like 10 minutes or so. Are there any questions? Also, I have some stickers up here. If anybody wants more stickers, grab stickers afterwards. Any questions?
Thank you first of all.
Thank you, yeah.
If you have questions, just use microphones. Here's our volunteers.
Hello, first of all, thank you for a great talk.
My pleasure.
Just, two questions. First, can you describe a little bit the most used use cases for using Elasticsearch? So it's obvious to use it in web shop for search. But for example, will it make sense for storing of a log file for doing troubleshooting, for example, for internal use? So what is the most common use cases which you made where Elasticsearch is used? And the second question, will it make sense to use it as a whole database? So not just storing the texts, but also storing all the other data, for example, to use like HANA, analysis, etc.
Right, so Elasticsearch started for search, and that is still one of the main use cases. So for example, if you're searching on Wikipedia, Stack Overflow, GitHub, behind the search box, there's always Elasticsearch doing the search for you. So that is kind of like the search use case that we have. The other thing that we then started are logs, because kind of what people figured out is storing logs is the boring part, and that is not what you want to do. You actually want to find stuff in your logs. So that's also kind of a search problem. And for us, search is the core kind of what we do, but in our opinion, a lot of problems that you have out there are actually search problems. So for example, logs, which we started with the ELK stack, Elasticsearch logs/Kibana, which we now renamed to Elasticstack, so we have all these components there. That is a very common use case to do that. I'm not sure if the most common use case, but it is one of the main use cases that people are storing their logs there as well. Because you probably want to search or aggregate stuff together in logs. And then people added metrics as well, because we can store metrics quite well, and it makes sense to combine that. And you might even add your business analytics there as well. So you have like one place where all of the data is combined. And then depending on which department you're in, you might build different dashboards to see different things, because the business people might want to see like how much stuff have I been selling today, and the operating people are more interested in like, okay, what is my response time and how many errors am I having and stuff like that. So it's kind of like nice to have everything, and you can combine it in multiple ways. And otherwise, oftentimes people have these little islands. You have one solution for this and one solution for that, and nobody talks to each other, and everybody's kind of on their own little island. And our approach is much more to have this common stack where you can do more stuff like metrics and business analytics. And we're every now and then adding new companies. So for example, we acquired a machine learning company recently to find anomalies in data. Or we added APM, application performance monitoring, to have like more deeper insights in your applications as well. So that is what we are trying to do, have like one stack where we have everything. For the question about the data store, there is actually a very common one. Let me quickly type. You can see I'm going to this place quite often. So in every distributed system, stuff can go wrong. And we're definitely no exception. And you basically have here this entire overview. So we have the data store recommendation, and then we have documented like these are all the things that can go wrong. And you will need to read through those to figure out, is this a problem for my use case or not? And then if you scroll further down, like you can see here, like this is a very long page. There's a lot of stuff that has been fixed in older versions. And this will just keep scrolling of things that we have fixed over time. And we're continuously improving in that. So in version 7, which will come out sometime early next year, hopefully, or later next year, but sometime next year, there should be some very good improvements around that again. Generally, our recommendation is it will depend on your use case. Or, you know, the answer is always it depends. So for example, if you store logs, probably the answer is yes, because what is the worst thing that happens if you lose yesterday's logs or if you lose 3 log messages? If you use like banking transactions, it's probably different, though it's not like we're frequently losing data or anything, but there are kind of like more labs-like scenarios where you kill one node and then you write some data and then you kill 2 other nodes right after that, where we could reproduce something where we could lose some data. But it's more like lab-like scenarios. It's very uncommon that that happens. The other thing that a lot of people have or expect, like, are you a database? So can you do SQL? We just added read-only SQL, but without joins. Or people expect transactions, which we don't do. So it will really depend on your use case. We are always like very careful, but we know a lot of people are using Elasticsearch as a primary data store for a surprising number of things. So for example, the most widely used online banking in Austria, where I'm from, they have like the old mainframe to store the actual transactions, but everything you see in the web interface, it's too expensive and slow from the mainframe. So all the data, they have been using Elasticsearch, I think for 5 years or more, to show everything in your online banking. And that is generally correct. Like, people would be very unhappy if their balance is wrong just a tiny bit. So they've been using that successfully for years. So there is a surprising amount of people who are actually using it for that. Sure. Oh, by the way, before we do the next question, I always try to take a picture so I can prove to my colleagues that I've been working today. Because they probably don't know where I am today. They normally don't. So, smile, everybody. Very good.
Attached to the invoice.
Yeah, right. So, any more questions? Anybody? Okay. Game over. Okay, no more questions. If you have more questions, find me afterwards. If you have lots of questions, it's fine. I had somebody yesterday who bought me a coffee, and I think we did an hour of consulting. We can totally do that. I'm here for that. You don't have to feel bad. Just come to me. Thank you.
Thank you.